week of class. And so hope that feels good to be nearing the end of the quarter. And so for this week, we're going to continue with our linear systems. And so, so remember that we're solving these systems that are AX is equal to B. All of these are matrices, okay, where we have an n by n matrix, and then multiplied by an n by 1, and we get out of that an n by 1. Our original way of solving this was saying that my X matrix is going to be equal to the inverse of my A matrix multiplied times the B matrix. But we decided that the inverse itself is just, it's cumbersome, okay? I mean, it's a really expensive computation. We end up with all kinds of calculation, round off errors, numerical errors when inverting the matrix. It's just not necessary to do. But instead, if we view our systems as more of a concept of AX is equal to B, then we've got to find some other ways that we can actually solve the system instead of just operating on the matrix and then multiplying it, or left multiplying the inverse by B. And so with this concept, this is also how just how in the future you're going to be solving systems, and also how you've done it in the past. So on Friday we talked about Cramer's rule. We've talked about elimination of variables, okay, which led us into Cramer's rule for that. And then today we're actually going to be dealing with the algorithm that we use for the left multiply, for the left divide function. Okay, because in this case, the syntax for MATLAB is X is equal to A backslash B. And so, so this works through an algorithm in the system in which we're getting into what's called Gauss elimination. Okay, so today is going to be one more step toward Gauss elimination, and then we'll deal with Gauss elimination specifically, the actual algorithm itself, on Wednesday. And is that right? No, Wednesday's WPA on Thursday and Friday. Okay, so that's what we got coming up to finish this thing out. Gauss elimination is a very intuitive process, I think you're going to find. And then what we're going to work with today is going to be specifically on triangular systems. And we have to understand really the beauty and simplicity of triangular systems to be able to put into play Gauss elimination. All right. And also understanding triangular systems sets you up for all kinds of other matrix operations. I said before that when calculating the matrix inverse, how we did it, we said, well, I'm going to take my matrix inverse, and I know that it's the adjoint of A divided by the determinant of A. Well, that's actually not the best way to calculate a matrix inverse either. It's actually to do something called LU decomposition, where you have a lower triangular and an upper triangular matrix, and then there's a way to calculate the inverse of the matrix by using those based on the inverse properties of the lower triangular and upper triangular matrices. Okay, now we're not going to go into that type of depth today, but in MATLAB and in other numerical libraries, that's the approach it's going to take. Okay, so knowing triangular matrices, and today we're dealing with triangular systems, not just triangular matrices, but understanding triangular systems, and it's important for lots of things. Okay. So let's jump into this. So triangular systems, they're a special case of our AX is equal to B form. Okay, and so this is this special case is defined by having all zeros, and there's three situations. In the first situation, it's 3 zeros above the diagonal. Of A. The second situation is going to be below the diagonal of A. And then Part C is both above and below the diagonal of A. So in our first scenario, where we have this being above the diagonal of A, this is called an upper triangular. And it's also known as a right triangular matrix or system. And so we'll say that's U. And what this looks like is that you have terms on the diagonal itself. So there are coefficients that are there in our system. And then we have numbers in that upper right-hand portion, and then all zeros. Oh, did I get this wrong? I sure did. I need to back up. Whoops. These are my lower triangles. Lower triangular. Pardon me. So if there's zeros above, this would be called a lower triangular system or matrix, also called a left triangular. All right. This is going to make a little bit more sense. All right. So my lower is defined by terms on the diagonal. We have all zeros above, and then we have coefficients that are populating the lower left. So you can see the triangular shape that the matrix is going to look like, and that would be our lower triangular. For B, this is our upper triangular. Also called a right triangular. And so for the matrix U, we have inputs on the diagonal. We have we have coefficient entries in the elements or elements in the upper right hand. And then on the lower left hand are all zeros. So you can see that this is, so this would be a right triangular. And we would write this as U x is equal to B. I'll go back to my lower. We would write this as Lx is equal to B. And then the last, we said if we have zeros both above and below the diagonal, we just call this a diagonal system. And so, or a diagonal matrix, we can put that as a big D. That's when we only have entries in the elements that are on the diagonal itself. Okay? Has anyone seen these before? Give me a thumbs up if you've done anything with these before. Okay, good. Okay, so maybe just one of you. All right. Well, what you're going to find is that these are nice and easy, okay? And you can already see that, at least I hope you see, that in the situation where we have a diagonal matrix multiplied times an X column matrix and equal to B, that each of these entries in X we can actually just do a dot divide where we have our matrix B and we do a dot divide with the diagonal of matrix D. Okay, so what does the dot divide mean? Remember, it's an element-wise division. And so we're just going to pick off each of the elements in the diagonal itself. Okay, and then to be able to get this X, it's going to be B1 divided by D11. Okay, B2 divided by D22. Okay, so that's the most simple entry that we have here. We talked about the diag function where you're grabbing the elements of each of, where you're grabbing the number that's in each of the elements of the diagonal. Okay, so if you can go back to your basic matrix operations, that was in there. So, so what I want to do is let's work through a system, and we're going to focus on the upper diagonal for this entire piece. Okay, and the reason why, as I mentioned, because we're moving into Gaussian elimination, and so Gauss elimination is based upon being able to convert your system into an upper diagonal. And so let's take the system where we have negative 2x1 plus x2 plus 2x3 is equal to 9. And then it's 3x2 minus 2x3 is equal to negative 1. And then 4x3 is equal to 8. And so in AX is equal to B form, then we get the matrix A being negative 2, 1, 2. And then 0, 3, and negative 2. And then our last row is 0, 0 for the coefficients of x1, x2, and then 4. x1, x2, x3. And then this is equal to, for our B matrix, 9, negative 1, and 8. All right, so let's go step by step on how to solve this. Okay, so using essentially elimination of unknowns. That's still the concept that we're working with, because excuse me, or in fact we're just going to solve and then substitute. We don't have to use elimination of unknowns, rather. So our first step is going to be to solve for the last unknown. And so by last unknown, we're talking about the last unknown in the column matrix of x's. And so that looks like this, where we just say it's x3 is equal to, and you see x3 is equal to 8 divided by 4. So let's keep all of our pieces here, where we've got our 8 and we've got our 4. And then, so we get that x3 is equal to 2. And so for our second step, we're going to substitute that unknown, so the unknown that we just solved for, which is the last unknown, into the next to last equation. So we're going to sub our last unknown into the next to last equation. Okay. So what this looks like is we have a 3x2, so 3x2 minus 2 times x3, which is 2, and then this is equal to negative 1. And so then we're going to solve for, and so we'll say and solve. All right, so we're going to solve for x2. And so we get that x2 is equal to negative 1. We're going to subtract a negative 2 times 2. Divide the entire thing by 3. And then by working out the arithmetic, we get that x2 is equal to 1. And so now that we solved for x3, we solved for x2. Let's move on to x1. And so our next step 3, I guess. Oops. is going to be to substitute the last and next to last, which this is a fun word if you know it. It's called penultimate. Right? You get your ultimate as the last, penultimate would be next to last. So if you ever pop up on a crossword puzzle or something like that, that's a fun one to know. Next to last, unknowns. Into the next, let's say, decreasing, right? Our next row or our next equation that's one more less, decreasing row or equation. Okay, so we know x3, we know x2. We need to plug that into our first row. Okay. And so writing this out, we get, so it's -2 x1, which we don't know, and then plus, it's the coefficient 1. We'll plug in x2 is equal to 1, and then plus 2 times x3, which is 2, and then this is equal to 9. And then we're going to solve for x1. And so still writing out the entire equation, we're going to take 9, which is on the right-hand side. We're going to subtract 1 times 1, and then subtract 2 times 2, and divide the entire thing by -2. And then this gives us -2. All right, so our final solution here is that our X matrix is equal to -2, 1, 2. All right, so that's that I hope you're seeing is just a straightforward, simple way to solve this upper triangular matrix. Okay, and by substituting, we're finding x3, we substitute in to get x2, substitute both those in to this top equation to get x1. All right, so let's now put this into MATLAB. And so, so when we put this into MATLAB, I want to walk back through what we just did by hand and start using our index notation, because in MATLAB, working with matrices, we need to use our index notation for implementing this. And so let's take a look at these guys, where x3 in this initial step, 8 divided by 4. And what we're doing here is we're saying, excuse me, that this is going to be this is B3, and then this is U33. Okay. And so B3 being 8, and then it's U in our 3, 3 position, right? So to make this numerical, we need to start thinking in terms of indices. And let's keep going here. So here for x2, all right, so we've got our -1. Okay, our -1 came from our, we can just do the entire thing. So this -1 came from this position, which is B2. And our 3 came from our U23 position, U sub 23. And then we have our -2 is coming from U, oh, got that wrong. Hold on just one second. That's not 2, 3, that's 2, 2. And then our -2 came from our U23 position. Right. And then, so we would get the equation here of x2. Write this out. So that x3, let's start with our x3. Our x3 being a b3 divided by u33. x2 is b2 let's see here, b2 minus u23 multiplied times x3, and then dividing everything by u22. Okay. Is everybody following me with this? All right, give me a thumbs up if you're following me so far. Okay, excellent, good. And then let's get that final equation for x1, where we have for x1, so our 9 is coming from our b1, and then we have our, let's go to our -2. Right, so our -2 is coming from u11. Coefficient 1 is coming from u12. The u13. And here, this is x2. This is our x3. Okay. And so when we rewrite this last equation, we get x1 is equal to b1 minus u12 x2 minus u13 x3, all divided by u11. So now when we put it into MATLAB, so I gave you some starter code, so go find your starter code on Canvas. And let's solve this system. And while you're pulling up your starter code, I'm going to collect all these onto one screen. So we've got x1 is equal to b1 minus u12, x2 minus u13, x3 divided by u11, x2 is equal to b2 minus u23, x3 divided by u22, and then x1 we said is b2, or b3 rather, divided by u33. Okay. All right, so let's see if we can keep this in view. All right, so we're given our upper triangular system, ux is equal to b, and this is our u and b that we had earlier. And so putting this into MATLAB, let's start by looking at the last line. So make a change there. I had that was x1, that should be x3. So let's start by looking at the last line, okay? And so when we're looking at the last line, so x1, which is in this form, then let's see if we can see what we're looking for here when coming up with these algorithms. This is only a 3x3, okay? But we should be able to see a pattern that's developing when calculating the answers to x1 and x2 and possibly x3. We'll see later that this is an exception. Okay, but in this pattern, if we look at the last line, then what you'll see is that when, let's say I is equal to 1, okay, and the reason why I say I is equal to 1 is because we know that when solving this system, we need to do something to each of the lines, okay? So let's say when I is equal to 1 using our index notation, and this is for when we're going to be solving for x sub I, then we see that x1 is equal to b1, well, looks like we already got it, b1 minus u12 x2 minus u13 x3 divided by u11. Okay, and so for our generic equation, where we're looking for I is equal to 1, x sub I is equal to bi minus, and let's write it as, in our index notation, ui, and then this would be I plus 1, right? Because it's u12, when I is equal to 1, it would be ui and then I plus 1. So 1 and then 2. And then we get an x I plus 1, because it's x sub 2, then minus u13. So this is going to look like u, and then it's I, and then I plus 2. Gets our u13, and then we have an x3. So that would be x of I plus 2. This entire piece is divided by u11, and so that would be I. So we've converted to index notation. Okay, so now there's another thing that we can see here, is that if we're trying to collapse this, use our index notation, but even collapse this even further into something that we can program using arrays, and this needs to be generic. Right now, we're not completely generic, okay? Because if we have like a 4x4, for example, then what's going to happen here is that this is going to be I plus 1, right? ui, I plus 2, I plus 2. And then this is going to keep on going, right? We would need to add a term to this that said, negative ui, I plus 3, and then x, I plus 3. And we're going to keep adding each of those terms until we get to the very end of to the largest dimension of that matrix. Okay. So our U matrix is an n by n. So what we have here is that we would keep adding each of these terms until we got to the end, which is an n, which is the dimension n. All right, does that make sense? Where we have, it's a ui, and then our second index for u is going to be n once we add in all those terms. And so what's nice about this is that we can rewrite our x sub I equation to look like this, where we have b sub I, right? That's going to stay the same no matter what unknown that we're dealing with. But for our b sub I, but for our x sub I, we can subtract our u sub I, comma, I plus 1, all the way to u sub I n, right, which we're seeing here, multiplied times the column matrix x I sub 1, all the way to xn. And because this is a matrix multiplication, we're multiplying each of these elements by each other and then adding them up. And so then the negative sign in front takes care of our subtraction that's in the numerator. And then in the denominator is always the same. It's u I. Okay. All right, give me a thumbs up if you're with me so far. Okay, I know that that could be a bit of a complicated step. Okay, so this is being recorded. You got your notes. You make sure you go back in and understand why this would be permissible. Okay, and so this is one of the more complex times that throughout this quarter that we're trying to kind of pull out or extract an algorithm from something that's there. And just a couple things I do want you to see is that even though this process, step 1, step 2, step 3, that we were working through here, that you're saying, this is pretty easy. Why are we doing this? Once you start transitioning into numerical methods, we need to be really careful about getting each of our indices correct. Okay, so that's the whole purpose of this exercise. And so, so keep that in mind when you're coming up with your own numerical algorithms. So our next step, now that we've got it in index notation, is to put it into a notation that MATLAB can handle. Okay, and so so as we look in MATLAB, let's type this in. Okay, so we'll keep this in light here. And so we're saying that we have an xi. So the index notation in MATLAB, we use our parentheses. So we have xi, and then we're going to have a numerator, okay, and a denominator. And in our denominator, it's always going to be uii. So when I is equal to 1, this would be the 1, 1 element of I. And so for our numerator, bi, and then minus, and we need to do our matrix multiplication, so it's u, and we're going to get all the terms in the ith, so it's the ith row, and then it's all the terms from I plus 1 to n. So this would be I plus 1 to n. And then we'll do a matrix multiplication times the elements of our X matrix that go from I plus 1 to n. So we use that same index notation. Okay, that's saying give me there we go. So give me these rows within our X matrix. So I plus 1 to n and u I plus 1 to n. U I plus 1 to n. Okay. And so we have this generic form, okay, or index form that's going to allow us to be generic. And then we need to put this into a loop. Okay, so when we put this into a loop, okay, what was the first one that we solved? Which was our first unknown that we solved when using our method here on our triangular system? It was x3, right? So if we're following our own algorithm that we did, or we're following the work that we did by hand to create this algorithm, then we need to start by solving for x3. So our indices will be 4, I is equal to 3, okay, which is also n. And then we need to go to 1 because we're going to solve for x3, x2, and then x1. And so to do this by going 3 to 1, we also need to give it the increment. So it's 3 stepping by -1 to 1. And so the last thing that we haven't done is we need to solve for n, which for this we can do the length of b. All right. Okay, so let's Save this. Okay, so we got n is equal to the length of b. We're going to go from n to 1. And then we came up with this generic equation that makes use of our matrix multiplication for solving each row. And so when we run this, okay, we get an error. So what is this error? All right, so it's telling us that we've got a problem in line 22. And in line 22, it has an unrecognized function or variable x. All right, so why are we getting this? So let's take a look at our equation. It's calling, when it gets to line 22, it looks like it's calling x, but we don't have an x that exists. So let's use our debug features. Let's click on this line number 22, which is going to have it stop in this loop. Okay, we press go, we press run. It's now stopped here. Remember, there's the K, which is allowing us to look and see what's in our workspace. And indeed, what we see here is that, you know, at this line, it hasn't run this line yet. It's going to call an xi, so xi, where I is equal to 3. But on the inside, or the right-hand side of the assignment operator, it's actually looking for an xi plus 1. And so, or an xi plus 1 to n. And so there is no x4, right? We don't have a fourth x, and even if we did, we hadn't solved for it yet anyway. So, so take a look at the way that we solved for xn. So let's look here. And the way that we solved for xn, n being 3, is in our first step, we used just b3 divided by u33, right? So for this b3 divided by u33, we didn't have access to, and we didn't actually need any of this more complicated numerator. We just needed the b term dividing it by the u term. So in our MATLAB code, let's do the same thing. Okay, let's initiate this by saying, all right, I'm going to solve for my x n term, and then I want to use my b n term, right, just like we have here. So when n is equal to 3, and then this would be n. So bn divided by u n. And then that way we already have a value for x3. So let's quit debugging and save our system again. And then now as we're coming in here, we have a value for x, and it's showing us that in the third element of x, we have 2, which is the right answer. That's what we got before. And so now when I is equal to 3, okay, it's now trying to overwrite the third element of x. So we need to make one change here. Because we've already stored a value into our third element of x, then it's not going to do us any good to start at 3. So instead here, we can start at 2, because we know that the equation for x2 and x1, or that this is the equation for x2 and x1. So x1, 2, and everything in the middle, but not xn. And so if we've done this correctly, then when we run this, it's like I've got a problem here. We have incorrect dimensions for matrix multiplication. And so let's find out what our issue is here. Let's debug it. So we now have I is equal to 2, n is equal to 3. We've been given u, we've been given our b. And so we have here bi minus ui. Let's try this out. So I, ui I plus 1 to n is -2, and then xi, I plus 1 to n is 2. So let's work that out. That's -4. Seems like that should work. So I'm just going through and I'm testing each of my parts because I'm actually not sure what I've done wrong. Okay, so it should like this. So let's run this line. X sub I. So we get a 2, and then we get a 1, okay, which is correct. And so it looks like the problem may be on our next round, next loop. So now let's find out what's happening. So oh, I think I see what we have. We've got a 1, 2. For that position, we have a 1 and a 2 for our x. So what's happening here is for our, let's go here. For this step, where we're taking our u1 and 2, and then we're multiplying it times x2, x3. Okay. We need our, we said here, we need this step to be a row matrix multiplied times a column matrix. But in MATLAB, what we have for this term for our x is actually a row matrix. Okay, so we have a row matrix multiplied times a row matrix. And so those dimensions aren't going to be compatible, right? We've got a 1 by 2 multiplied times a 1 by 2. And so to make this a 2 by 1, we can put in our single quote, which is going to do the transpose. So let's save this. Let's run it again and just see what happens. All right, that's great. So what we have here is it ran, and then in our display, we're displaying x, which is -2, 1, and 2, and we can even display this as a column. Okay, -2, 1, and 2. All right, so I had to troubleshoot some matrix dimensions there to be able to make this happen. Okay, so one last thing I want to talk about is that now that we've debugged this and put this in a generic form, is that this algorithm is called backward substitution. And so this backward substitution is incredibly important because it's going to tell us if we can come up with a system, or it tells us rather, that if we can come up with a system that looks like this, no matter how big the system is, that we can solve the system using this simple algorithm. Okay, so on a Wednesday and Thursday, we're actually going to figure out how to change this system into a system that looks like this, where we have an upper times our x, and then I'm going to call this b prime because these two aren't going to be the same. We're going to have to alter our b. Okay. Also, a lower diagonal system has something called forward substitution, which operates on a similar principle, but instead of starting with your later terms in x and working back, you start with your early terms and work forward. Okay, so then the very last thing we need to talk about of why this type of system is helpful is that, based on our discussion last week about system conditioning, we need to know whether a system is solvable, because even if we've got a triangular matrix or a triangular system, we may not know that it's solvable. We need to know that by taking the determinant of the system. So we're still going to be operating on if the determinant of u is equal to 0, then there's a singularity. So let's calculate the determinant of our system that we're working with here. So -2, 1, 2, 0, 3, -2, 0, 0, 4. And so getting the determinant, it'll be -2 times the determinant of the minor, 3, 2, 0, 4, and then subtracting 1 times the determinant of the minor that's left over, 0, 2, 0, 4. And then plus 2 times the determinant of its minor, 0, 3, 0, 0. Oops. And so this determinant is -2 multiplied times 3 times 4 minus 0 times -2, and then minus 1 times 0, then plus 2 times 0, because there's a 0 in both of those rows. And then what we see here is that the determinant of u is equal to only the multiplication of these three numbers. So we get -2 multiplied times 3 multiplied times 4, which it gives us 24. But the important part here is that these three numbers, -2 and 3 and 4, are found in the diagonal of this triangular matrix. And so it's just the elements that are multiplied times each other that gives us the determinant of the matrix. And so whenever you have a triangular matrix, whether it's diagonal, upper triangular, or lower triangular, to get the determinant, you're always going to be permitted to just multiply through. Okay? And you'll see that to get this determinant in MATLAB, we use the prod, so the product of all the elements that you put in here, so the product, and then you'll put in here the product of the diagonal of u, which picks out a matrix, in this case a 1/3 matrix, multiplies each of the elements together. And so you can see really quickly when you have an upper triangular or a lower triangular that if you have a 0 in the diagonal of an upper triangular, lower triangular, or a diagonal matrix, that it's going to be a singular matrix and you won't be able to solve the system for a unique solution. Okay, so this is true for all triangular matrices, and gives us another reason to want to put our systems into this form, either an upper triangular, lower triangular, or I mentioned the LU factorization or decomposition earlier, where we have a lower multiplied times an upper in some more advanced type things. Okay, so on Wednesday, Wednesday's the WPA. On Thursday, we're going to figure out again, how to get our AX is equal to B into this UX is equal to a new B column matrix, and then we'll be able to apply the back substitution, and then that is the primary algorithm that's being used for our left divide that MATLAB uses. Okay. All right. So for the practice problems, you're going to take this loop that we just now created and turn that into a function. So turn it into a function with the error control, warning control that we use for Cramer's rule, and then you're going to solve several problems out of the chopper book that you're going to take a full matrix and then convert that into an upper triangular matrix simply by chopping off the lower triangular portion of that matrix and looking at the system conditioning and using your function to solve those systems. Okay, so as you're looking through this, go back through that algorithm that we just created really quickly today, and make sure that you understand each of the steps and why it works. So why this algorithm is appropriate to be used for an upper triangular matrix. All right. Oh, somebody in the chat. Would it need to be, since it's a matrix operation? So Brooks asked a good question. And this is when we were doing the troubleshooting. It was suggesting the dot divide. That wasn't necessarily where it needed for it to be. Remember, it was in the multiplication that was what mattered, and it was simply because the matrix dimensions didn't work. So if you get that error, it doesn't always mean that you need to have a dot divide or a dot multiply, but it's also saying I can't do this matrix multiplication. Okay, you may need to, in this case, check your matrix multiplication? That's a good question, Brooks. All right, y'all take care, and we'll see you on Wednesday for the WPA. Come to office hours with your questions.